Hi, and welcome to another conversation with Even More, a podcast where I have insightful and sometimes fun conversations with mavericks, mystics, activists, creatives, healers, and change makers. And today it's part two of our conversation with Ramone J Campbell, who is leaning backwards rather than forwards. I'm not sure why. Um, if you want to watch part one, you just go to Conversations with Eve and More on YouTube or wherever you listen to your podcasts, and you'll be able to hear his full bio on there and hear his theories of influencity and whatever else we talked about that day. What was it? The second thing?
I think it was the same relativity.
Ah, that's right. Yeah. It was a very interesting conversation. So do go and check that out. Today, Ramone, who has a book coming out at some point soon. What's that called, Ramon?
It's called the Philosophy Mathematica, in
That's
short.
right. Yes.
And
I'm not
it's
ready for you to tell me about it yet, just telling them about it. So he's got a
right.
book coming out. You can tell us about that a bit later. But today he is going to be having a conversation with me about Derivatus, which is his new branch of mathematics that he has created, and also the theory of quantum gravity. And as I'm not a scientist or a physicist,
Physicist, yeah.
can't even speak. I'm not a physicist. My role here in this conversation is to try and answer questions based on someone who's new to the field and wants to understand. But I'm sure Ramon will go into deeper levels of the topic during the conversation. So tell me, first of all, Ramon, what is so different about derivatives as opposed to other branch of mathematics?
Well, basically, derivatus is the solution to calculus. Because if we examine calculus properly, the whole basis of calculus is the limiting process, the process of ascertaining the limits of functions, right? So if you have something like f of x as the, as the limit, with the limit as x approaches some arbitrary numerical value, it says x approaches that value, but x is not equal to that value. If you understand what I'm saying.
I don't,
X is
but
not
I'm
equal
going to
to
nod like I do. I have no idea what you're talking about.
that. Okay. So if it says the limit as x approaches 8, right? Usually they would take the 8 and they would plug it into the equation or the formula where everywhere you see x, you replace x with 8 because x approaches 8. What I figured out is that simply because it says x approaches 8 or any other arbitrarily chosen value, numerical value, doesn't necessitate the notion that that is the value that is supposed to put there. Because it says x approaches that value, that numerical value. X is not equal to that value. X is not equal to 8. Isn't equal to 10. Isn't equal to 24, etc., etc., etc. So I developed my own way, and I'll show it to you here, a little bit of it. I developed my own way, and this is the formula here for it. My own way of ascertaining the precise limits of functions. And I'll read a bit of it to you, just to give you a bit more perspicacity into the topic. The subtitle is On a New Determination of Ascertaining Exact and Precise Limits and Continuity of Functions. The notion of a limit translates into that of the belief that x is getting as close to a value as possible, but never reaching to that value. Let us assume that you want to park your car in front of a wall. You inch closer and closer to the wall with the car, but you never crash into the wall. Therefore, the smallest gap betwixt the car and the wall is the limit as to how close the car can get to the wall without touching the wall. Henceforth, the calculus notion that the given numerical value of limits should be substituted into values for x or whatever variable we are working with is erroneous and flawed, as the value is just a mere approximation to the real limit. Let us assume that we have the function f of x equals the limit as x approaches 8. We ascertain the exact limit using the following formula, and then I gave my formula, which is f of x equals the limit as x approaches 8, x cubed plus 4x plus 3, all divided by x plus 4. And then it continues from there. So everywhere where you see x, you put the exact value for the limit into that function. And how do we get the exact value for the limit? We follow up by saying x cubed plus 4x plus 3 minus open bracket x plus 4 close bracket equals p over q, and p over q is going to be defined now, equals, p over q is equal to the limit as x approaches 8, 559 divided by 47 multiplied by 4 equals 559 divided by 188 equals 3. So we have a number now. That's not the limiter. That's just the number we're going to use to plug into the original formula that we started with to ascertain what the limit would be. So we say, because you remember the original formula was the limit as x approaches 8x cubed plus 4x plus 3 divided by x plus 4. So we get 3 now. We got the number 3 there. So we're saying 3 cubed plus 4 times 3 plus 3 divided by 3 plus 4 equals 6. Hence, the limit as x approaches 8 is 6, a value that is close to 8, but not 8.
Okay, so how did you come to that calculation?
Well, basically by studying the calculus and, seeing, because with me, what happened with me is that I could go to the shop to purchase something, and somebody else will be purchasing something in front of me. And this is a real true story. If a man is buying something in front of me and he tenders $10, and the object that he is buying, the good that he is buying costs $4, then he has to get back $6 change, right? So from that, I would see a mathematical pattern immediately and develop a new mathematical theorem just based on that interaction. And say, well, if 10 minus 4 equals 6, then if we add 2 to the subsequent number, and we say 4 minus that subsequent number, we're supposed to get a number that's a little bit greater than 6. So 6, 7, 8. 4 from 8 is 4. I have the theory written down here. I should have brought it out. Just give me 1 second.
Should we keep ourselves amused while he's off finding his stuff? Well, I've had a very interesting day. I don't know about you guys. How's things with you? Really? That's great.
Yes.
Oh, he's back.
Yes. So basically, this is the formula here I have that I got from that interaction. So the equation I got from that experience was open bracket x plus n minus 4, close bracket equals a, right? So we start off by saying 4 plus 2 minus 4 equals 2, because 4 plus 2 is 6, and 6 minus 4 is 2, 4, 5, 6. Then we say 4 plus 4 minus 4 equals 4, because 4 plus 4 is 8, 8 minus 4 is 4. 4 plus 6 minus 4 equals 6. Then we say 4 plus 8 minus 4 equals 8. And then we say 4 plus 10 minus 4 equals 10, and so forth and so forth. And it says here, using I call it cumulative subtraction. It says here, using the cumulative subtraction method, each answer is a multiple of 2, and each number we add to 4 in our calculation is also a multiple of 2. So if you know, this is how the answers flow. 4 plus 2 minus 4 equals 2. 4 plus 4 minus 4 equals 4. 4 plus 6 minus 4 equals 6. So we get the answers in this sequence 2, 4, 6.
So what happens if you've got an odd number?
Well, I haven't tested it out in that regard as yet, but I highly doubt that this formula would apply to odd numbers. I highly doubt so. I mean, I could be wrong, because when I tested, I could see that it works fine the same way. Because it's arithmetic, it's math.
Yeah, I just wondered why you chose even numbers and -4, for example,
Right.
to work
The
out
reason I
this
chose
equation.
-4, the reason I chose -4 is because the man in the shop, he paid $4 for his good,
Mhm.
and he tendered $10, and I left him with $6. So I chose 4 to be a constant, -4 to be a constant in the
Okay.
calculation.
But it could
Yes.
be another number.
It could be.
Okay. And in parts of the equations that you read out, obviously I can't recall all of it, but
Right.
why is the number cubed and not squared or something else?
Well, I mean, it could be squared, it could be raised to the 4th power, to any power. But for this particular calculation, we said x cubed.
Mhm.
So it doesn't matter if it's cubed or it's squared or it's raised to the 4th power, but it all depends on what you're trying to accomplish.
Okay. So
Yes.
it would only be for this specific version of the equation, but you
Calculation.
could, right, okay, this calculation.
Yes. Yes.
Okay. So how does that differ to what was already there? Apart from it's more accurate, but really, why haven't other people come up with a more accurate version? What's so groundbreaking about this?
Well, I believe that everyone or most people in the world, or 99% of the world population who studies calculus or does a mathematics master's or PhD or any qualification in maths and studies it at university, I believe that they are content with just absorbing already accepted knowledge and not trying to challenge the status quo, not trying to change the game, as we would say. They believe that every information that they are being fed, they swallow every pill, and they never question things. And this is what differentiates innovators from average-minded people, or people who just want to get by. They just want to get a degree so they can get a job as an analyst or engineer or whatever the case may be, because calculus shows up everywhere. Calculus shows up in economics, it shows up in engineering, it shows up in chemistry, it shows up in physics. Well, obviously, it's a branch of mathematics. There's integral calculus, there's differential calculus, there's multivariable calculus, there's even tensor calculus, there's vector calculus. I mean, calculus is a very broad subject, and it has many applications. And that means that since I have found a more precise version of it, that my branch of mathematics could then too be applied to all subjects.
Understood.
And that's what
So
will be
can it be
spoken about in the
used?
book.
Yeah, so that's what I want to ask about a little bit more, just to see if I've got this right. So can this be used to calculate the exact dimension of the space-time curvature? Can it be applied to that? Was that your original focus, or was it just general?
Well, I mean, in my quantum theory of gravity, I use 3 different branches of mathematics, right? I use differential calculus, I use integral calculus, I use multivariable calculus. And the 4th one, tensor calculus. So basically, if we want to calculate the curvature of the space-time, we have to implement tensor calculus into that whole system to bring it to fruition. But I have investigated and I have found a way to use differential calculus and multivariable calculus to assist in calculating with the curvature of space-time. Because in my equation, my field equation for gravitational attraction, the first few terms, r mu minus 1/2, right? That term alone, there are tensors involved in there. It's the Ricci scalar curvature, the Ricci curvature tensor, excuse me, and that shows up in Einstein's field equation for gravitational attraction as well. So my equation is a derivation of Einstein's equation based on Einstein's equation. It comes from Einstein's equation. It's built upon Einstein's equation. It didn't come out of thin air.
Mm-hmm.
So I actually ascribed a differential calculus mathematical model to that Ricci curvature tensor to have innovated my own way of calculating the partial curvature for the gravitational framework in space. Because I'm calculating how the gravitational framework curves ascribed to the presence of the mass and the spin of the planetary bodies in space.
Mm-hmm.
Because if you look at Einstein's theory of general relativity, his theory of gravitation, his theory of gravity, it's the curvature of space-time. Curvature is the operative word there. Because my theory of quantum gravity says there is curvature in the universe that yields a gravitational field for the planetary bodies, but just that it's not space that is curving. It's something that's composed of particles, and that is the gravitational framework. Now, what is the gravitational framework? The gravitational framework is the body of the trillions and trillions of small quantum particles called gravitons that act together, and they react to motions within them similar to the way in which water molecules react to motion within it. So if there's motion within the gravitational framework, there are the ripples, gravitational waves. So gravitational waves are real. Einstein was right about that. But what he was not right about is what yields gravitational waves.
See what you're saying. The reason I asked you that is because you were saying that this derivatus has this ability to be more accurate. And I wondered if it could then be applied to create more accurate measurements of the curvature.
Yes, it can. Yes, it can. Absolutely. Absolutely.
Okay.
Absolutely.
How would that apply? Not literally, you can't calculate it right now, but you know what I'm saying? I mean, what would be the impact on science or physics or astronomy or whatever if you could more accurately calculate the curvature? What would it allow people to do and discover, do you think?
Well, basically it would give us deeper insights into how gravitation works. It would give us a more precise measurement of how the gravitational framework is curved around a planet in space. It could let us delve deeper into ascertaining the strength of the gravitational field of any planet by nanometers of accuracy, and therefore help us gain a better perspective on gravitation on a whole.
Mm-hmm. Might it
and
help
it could make
us?
Great predictions too.
Might it help us with time travel?
Well, that's a whole other theory that I did.
You did?
Yes.
Wow.
Yeah, that one involves because you see the thing with time travel is that Einstein stated in his special theory of relativity in 1905 that only a body that has zero rest mass, that is massless, would have the ability to travel at the speed of light. And Einstein said that the speed of light is the cosmic speed limit in the universe. Nothing goes faster than the speed of light, because it will require more and more and more energy to accelerate faster and faster and faster. And because the speed of light is such a great number, it would require an infinite amount of energy to propel to the speed of light, which is impossible. That's what he says. But I cooked up something that kind of negates and contradicts that, but that's a whole different conversation, maybe a part 3.
I don't know if I can cope with too much brain power here, but yeah, that would be fun to calculate.
Yeah, I mean, yeah. So basically, to get something to lose mass, right? You have to drop it from a height. If you do research on that, you'll see what I'm talking about. How do you make something lose mass or become massless? You drop it from a height. Now, what I deduced is that if me dropping my phone from a height would reduce its mass, What if I dropped it from a height that's proportional in numeric value to the amount of mass that it has? If I do that, it would get enough time to lose all its mass. If it loses all its mass, then we can propel it to the speed of light. And Einstein said if it would be able to move at the speed of light, time would go backwards relative to you. You'd go back in time. Time would go
But
backwards.
how high would you have to be?
No, actually, if it light, time would stop. That's what he says. Time would stop. If you go faster than the speed of light, time would go backwards.
How high would you have to drop it from then?
Well, if an object weighs, let's say, 5 kilograms, you drop it from 5 feet.
That's quite small. I was expecting it to be bigger. To be
well, that is a small
stopping time from 5 feet.
That's an arbitrarily chosen number. I mean, if it weighs 100 kilograms, because we don't say pounds in physics, we say kilograms and mass and stuff like that, and weight. If you drop it from 100 feet, then it's going to become massless. That's my theory.
Oh.
That's my hypothesis, my extrapolation. Excuse me. We haven't tested it yet to see if it's true or false, but I'm pretty confident about the results when it's tested.
Okay. So let me bring you back to what you're here to talk about.
Right.
What haven't we talked about with regard to derivatives that you want to share? Because you've read out the equation and you understand what each point in that equation is, but we do not. So do you want to talk more about what each element of the equation actually means?
Sure. So f of x means the function of x. The function of x. And the limit, it follows by saying the limit as x approaches 8. So therefore, if it was the regular calculus, the function of x would be 8. So it'd be f of 8. Or f of x equals 8. And then you plug 8 everywhere you see x in the equation. So you have 4x, you say 4 multiplied by 8. You have x cubed, you say 8 cubed. You have x plus 4, you say 8 plus 4. And then you have the plus 3 on top of the numerator. Then you have the where
What's
you have
the
the 8
numerator?
everywhere with x. That's the top part of the fraction.
Okay.
And the bottom part is called the denominator.
Okay.
Yeah.
Carry on. Yes.
Yes. So basically, the limit as x approaches 8. That basically means what I explained and read out here in the first aspect of this conversation, with the car getting as close to the wall as possible. There's a limit as to how close the car can inch towards the wall without touching it. And that explanation in itself confirms my formula, because it says as close as possible to the wall that the car can get without the car touching the wall. So if x approaches 8, then it reaffirms my notion that x is not equal to 8. And the answer we got for the limit is 6. So the closest the car could get to the wall without reaching 8, or the closest I could get to 8 without reaching 8 is 6.
And what would happen if it was 7?
Well, nothing really would happen. It would
just hit the wall.
If it reach 8, it will hit the wall.
Okay.
Yeah.
Okay.
Yeah.
So I'm trying to, because I can see how your mind works, is that you use real-time stimulation, encounters, environments to come to your insights. It feels like there's like inspired thoughts that just like pour through you that are triggered by everyday events.
Right.
Is that something that you feel is lacking in the world of science and physics and maths, that people, the ones at the top tier, can be far too academic and not allow real world stimulation to generate new thought, if that makes sense?
Well, mean, that's how science works. That's how physicists and mathematicians think, or mathematical geniuses think. If you do research and you type in the question in Google, what are the traits of mathematical geniuses? You would see that it would say that these geniuses they see connections in numbers and patterns, and they pull from everyday experiences, they innovate, they're innovative and stuff like that, and they think outside the box.
Okay.
And everything they said there, I could relate to.
Because the reason I'm asking that is I do get a sense, partly of what you've shared, of people get very, they stay in their comfort zones. So if they've reached a certain level of expertise, or there's a certain agreed upon theory, it doesn't matter whether it's in science or maths or medicine or whatever it is, psychology, people get very resistant to new ways of
ideas
and new ideas. So have you found or seen any resistance to your ideas from the academic community?
Actually, not that much. I would say that only one person is putting up some sort of resistance, but he's not really that significant because he doesn't belong to any university. He's not a professor. He's just a CXC mathematics teacher. But he never studied calculus at university. And usually these CXC mathematics teachers, they actually did study calculus in depth, whether at university or on their own. Like me, I studied on my own. I actually teach math in my spare time. I help students with their math, with their basic mathematics for CXC secondary school, right? And I make money from that as well. But my main trade is my art. You know, I create miniature model houses using cement and miniature bricks. I've actually engaged with you know, the Prime Minister's office in Dubai. That's the Sheikh. That's Al Maktoum, Prince Al Maktoum. Yeah, so to create replicas of his landmark buildings in Dubai. But I'm straying off topic here. I'm digressing. But let's get back to the topic.
Yeah.
So one guy is giving resistance, and I wouldn't call his name. Don't want to make him relevant or anything like that. But he's saying that, you know, I should go and get my degree in mathematics. He doesn't have a degree in mathematics. He took like 8 years to finish a 4-year degree. That's what he told me. So I wouldn't really take him on or, you know, be too bothered up by what he says. And then when he's saying that, you know, show him proof that the professor from UV said that my derivatives is correct and my mathematics is correct, and that professors from abroad said that my physics theories that challenge Einstein is correct, I sent him these screenshots of the emails. And then he was like, oh, well, whatever. So I don't know if that's ascribed to jealousy or resentment, that he's a teacher and he out here longer than me, he's older than me, he's in his 40s. He's supposed to be smarter than me in his mind and know more than me. I'm just a snotty-nosed little boy in front of him in his mind. What you doing knowing more than me? Or being better than me at this, or having more perspicacity into the subject than me? But, you know, I told him point blank, I said, having a lot of knowledge on any subject matter doesn't really say anything much. It's what you do with that knowledge to innovate and make new things. Building on that existing knowledge is what really makes the difference and makes you stand out. The Einsteins, the Newtons, the Galileos, the Michael Faradays, the Marie Curies, all these great scientists, they used existing knowledge to build their theories, and they won Nobel Prizes as a consequence. And I am confident that one day I will win the Nobel Prize in Physics too, because I've actually gotten a response from NASA's headquarters via email. They sent me some links to some websites where I could facilitate them with the intricacies of the steps within my experiment in my quantum theory of gravity and how to go about detecting the graviton. I think I told you about this already. And I'm moving forward with that. So if they come back proving me right, that would be an instant Nobel Prize for me. And NASA would share any credits too because they assisted, they did the experiment.
Yeah, I'm thinking about that one naysayer. If you do become recognized on the world stage, you're going to have to deal with a whole other level of that because you'll
Yes,
be challenging received wisdom. So,
yes,
shall we move on to your theory of quantum gravity in more detail?
yes, we shall. Yes, we shall. I have it here.
Okay.
That's the last page. And this is the first page. Yes. So perhaps I can read the abstract to you so you can get an understanding of what it's about.
Yes.
Or the introduction, I should say. It says here, our current understanding of gravity today is based solely on what Albert Einstein put forward in his theory of general relativity over 100 years ago. The notion that space itself is bent by the presence of mass energy by the planets. In this paper, I endeavor to demonstrate to the scientific community why Einstein's notion of what precipitates gravitational pull is ultimately erroneous, and why my new quantum theory of gravity supersedes the old notion of gravitational attraction. What I also endeavored to demonstrate in this paper to the international scientific community is the corroboration of the notion that gravitons exist. In this paper, I endeavor to demonstrate the effects of weightlessness due to free fall, a phenomena I refer to as gravitational sinking. This paper also outlines a better explanation of the phenomena that is gravitational time dilation, and my advanced version of the equation of gravitational time dilation is given here. In addition, I introduce what is the fourth law of motion in this paper, which gives us a better perspective of why the planets spin on their axes as they orbit around the sun.
Okay, well,
So
that's
what
a
did you
lot.
gather from
I gathered that you use a lot of words that I don't understand quite a lot of the time.
them?
Now, I do remember the gravitons. I do remember that you derived that by looking at water in a bottle. That
Yes,
much I remember.
yes,
And that this theory of quantum gravity essentially proves that gravitons do exist and move it from an hypothesis to an actuality. Is that right?
correct, correct.
Okay. So, what do you want to tell us about this groundbreaking thing, this equation that you have come up with? Do tell us what the equation is.
Well, equations.
Or the calculus. Yeah, obviously there must be more than one. Yes, sorry.
There are a lot of equations. And I
Mm.
can show them to you here before I get into it. So these are a few here. This is my equation for calculating the energy of a graviton. This is what would actually prove the NASA experiment would prove how NASA would prove gravitons exist. Because if we are able to detect an energy release from a source, there must be a source. And if the
Can
theory
I
says the
say
source is,
something to interrupt you?
yes, you can.
That equation looks very pretty to me. Does that sometimes determine whether an equation is more accurate because it looks pleasing to the eye or not?
Well, I mean, there are some ugly equations that are correct.
Okay.
Huh?
Okay, go ahead, carry
And
on.
then there are some beautiful looking equations that are wrong.
Okay.
So, but it's interesting you would say something like that because we physicists and scientists and mathematicians, we actually see our equations as works of art.
Mm-hmm.
I mean, I remember Michio Kaku was in an interview at one time with CNN. He was saying that the first time he looked at Albert Einstein's equations of general relativity, he cried because they were so gorgeous
Mm-hmm.
to the eye. And I tried
See,
to follow in Einstein's
I
footsteps.
obviously had the same eye.
That's interesting. You would actually say that though.
Mm. Yes,
And this
carry
is
on.
my equation for gravitational sinking, this equation here.
Mm-hmm. Go and read
It
that one
shows
out. I
that
like that one. Read that.
it shows that well, let me read it out to you.
Mm.
Or do you want me to start from the graviton
Yes,
equation?
start from that one.
Let me start from the graviton equation. The graviton's collision with the molecules of liquids, gases, or solids yield energy released. The gravitoelectric effect, that's what I call it. Like you have the photoelectric effect, photoelectric effect. Gravitons themselves carry energy. This is kinetic energy. You ascribe to their motions, right? Because kinetic energy is the energy a body possesses due to its motion. The more motion it has, the more momentum, the more kinetic energy it will have. That's why a baseball or a stone thrown to the air would break a glass. With the more force it throw it, it will break the glass even more or faster, or it will impact it with more force. That's kinetic energy release. Right? When a graviton collides with a molecule, this collision precipitates the release of small packets of energy in the form of kinetic energy. An experiment which is synonymous to the experiment carried out to detect the energy of a photon may be carried out to detect the presence of kinetic energy yielded by the graviton molecular collisions, where a circular metal plate is utilized. So what would happen is that in a dark room, because you want to make sure that no photons, which are the particles that make up light, are bouncing off of the metal plate. The metal plate will collect the gravitons, and the molecules within the metal plate that make up the metal plate, they would actually vibrate as a consequence of the collisions of the gravitons into them. And this collision would release the energy that would bounce back off on the other side of the circular metal plate. And that is what NASA is going to measure, try to measure, to ascertain if, because if we see any energy being released without light on, no photons colliding with the plate, so where the energy coming from? What did Campbell's theory of quantum gravity say? It's coming from the gravitons colliding with the molecules of the circular metal plate. So if they detect the energy, then that is indicative that there's a source to that energy, of that energy. What is the source? The gravitons colliding with the molecules that make up the circular metal plate. And therefore, if they actually do measure that energy, which I am sure that they will, because I did my work, I did my studies and my research, and I worked very hard at it. I am sure and certain that they are going to discover that these gravitons do exist, and we are going to make history together.
Where did they come from?
That's a very interesting question. I think we have to take it to prayer and go to God with that. All I know is God created them. A benevolent being, God, created them. He created everything. He created the universe, he created the sun, he created the rain, he created water, he created us. And then the scientists want to ask, where's the evidence of God existence? Look around you. You woke up this morning, didn't you? So it goes on to say, the energy released via graviton molecule collision is given by, and then the equation is read out here, E for energy equals the integral of open bracket g pi r squared plus hfc squared, where h is Planck's constant. Pi
H is
well,
what?
pi.
So slow down.
Planck's constant. Max
What's
Planck's
that?
constant. Well, basically, it's a number for calculating things in physics. Different things in physics, right? Einstein used it in his photoelectric effect, actually, his equation, right? So I reused it in my equation since the experiments are similar. It's similar, they use similar apparatus, you know? C squared is the speed of light, F is the frequency, divided by M over V. M is the mass, V is the velocity. Dx, that's what we integrate with respect to. 4, gravitons flow through everything. A bottle half filled with water with a cap covering the bottle will still have the water stabilized inside the bottle. A person and objects inside a room will still be perpetually impinged to the ground via the force of gravity, regardless of the fact that there is a roof segregating them from the outside. This is a result of the tiny graviton particles flowing through all solid matter. This revolutionary insight shows that gravitons do in fact exist. So you see how it
Okay.
works there. Yeah.
Kinda.
And the second equation I wanted to hear about now is gravitational sinking.
Mm-hmm.
Gravitational sinking, a freely falling body will not feel its own weight, and Einstein actually made this promulgation in his theory of general relativity, this law, the scientific law, that a freely falling body would not feel its own weight, and that's actually corroborated by experiment. If you're in a plane, they actually do this thing where they put people in planes, and they make the plane free fall through the air.
Mm-hmm.
And the people inside the plane would actually become weightless inside the plane and float around inside the plane as if they were in outer space.
Mm-hmm.
And that kind of ties into the same theory of quantum gravity in this theory where I extrapolate my notions on why there's no gravity in space. And I'm saying it's due to our entire Milky Way galaxy actually rotating around a supermassive black hole and falling towards that black hole. So since everything around us and everything that we can see is falling, and Einstein said that when you're free falling, you become weightless. Then when an astronaut goes into outer space and looks like he's floating, he's actually falling towards that supermassive black hole.
Really? You can't just throw that out there. Is that actually a thing?
Well, I heard Neil deGrasse Tyson spoke about something similar to that. Didn't go as in depth as I did, but he did say that. He said that it's essentially falling in space. That's what he said. And I was like,
Yeah,
hey,
so
all right.
it's when did the black hole part kick in? That you can't just throw that in. We're all falling into a black hole right now. What's going on?
Well, I mean, Einstein's theory of general relativity predicted the existence of black holes, right? There are these things that
I know
the
what a black
gravitational
hole
field.
is, but I'm just saying in relation to this theory.
Well, right. Well, that's how the entire universe system works. Everything is orbiting around something else. The moon orbits around the Earth, while the Earth orbits around the sun, while the sun orbits around a supermassive black hole.
Mm-hmm.
That's how it's like gear wheels in a clock.
And this is
One
proven
gear
or
wheel,
just theory that there's a supermassive black hole that the sun is
proven,
full?
proven,
Okay.
proven. Scientists have already proven that. They already
Okay.
observed it with their telescopes.
And so when will we all be absorbed into
I think never.
it?
And my theory actually shows why.
Mm.
Because if you have a cake mixer, right, that's on, just one blade in, and that blade is spinning in the water, in the bowl.
Mm-hmm.
Ripples are being sent out from that blade, the core of the spinning of that blade, while the blade is synonymously pulling in water in towards it in the same direction as it's spinning.
Mm-hmm.
If I put a clay ball in that water, in that spinning vicinity, the clay ball would orbit around the spinning cake mixer blade, just like how the Earth orbits around the sun. And remember, I did say that the gravitons behave like water. So the closer and closer and closer the cake mixer, the clay ball gets the cake mixer blade, is the stronger the pull would be upon it. And the closer and closer and closer the Earth gets to the sun, the stronger the gravitational field would be upon it because the pull is stronger at a shorter distance. That's because it's closer to the source. These gravitational waves that are being sent out simultaneously push back on the Earth, therefore preventing the Earth from colliding with the sun. So the closer it gets, the stronger this resistance becomes. The waves pushing out
Mm-hmm.
and pushing against the Earth. So they would actually spin fast, and speed up to its maximum, and then go back out into orbit again, far away from the sun.
So
Just like the
I'm
cable would do.
sorry, but this is quite interesting to me. If you wanted to prove that the universe was intelligent, wouldn't then gravitons be the perfect example of why we aren't all colliding into each other because there's a divine intelligence that
Yes.
created something like a graviton to
Yeah.
ensure that we
Yeah.
couldn't be destroyed?
Right. Yeah, it could. It could. I mean, there are many implications with my theory. The theory has a life of its own.
Mm.
I mean, physicists will understand my theory better than me 100 years from now than I understand my theory today. because they are going to build on it and spawn new ideas. They're going to do research. They're going to build apparatus for experiments to confirm even more parts of my theory. And it's actually been published in a few weeks, by the way.
Yeah, that's exciting.
That's
I'm
exciting.
still struggling with gravitons being massless because.
And remember the question you asked me, if gravitons are massless, then if they collide with something that has mass, do they gain mass? Remember you asked that question?
I didn't ask if they gained mass, but I did ask how can they influence anything without mass?
Oh yes, how can they influence anyone? Well, this is ascribed to kinetic energy again. When the gravitons collide, the kinetic energy of the collision is transferred from the graviton to the molecule of matter, and this therefore causes its motion.
Okay.
That's
and in terms of the supermassive black hole, don't you have to have mass to be pulled into the black hole?
Actually, no, because light itself can't escape the gravitational pull of a black hole because the gravity is so strong and light is massless. Photons are massless.
See, okay, good.
Yeah.
Good. Thank you for that.
I did my research.
I did answer a good question. I'm fascinated by these things. So, what other equation do you want to share around this, if any?
Right, I'll share my
We have 8 minutes to go.
8 minutes, perfect. I'll share the fourth law of motion and the equation associated with that. This is the equation associated with the fourth law of motion. You know what, Newton gave us 3 laws of motion, right? You heard about that. I know you heard about that.
We've all heard about that, I'm sure, somewhere in our lives.
Somewhere in our lives. So it goes like this. I always wonder why I sweat so much when I'm on a podcast with you.
I don't know. Maybe I'm challenging you.
No, maybe it's exciting.
But I doubt
maybe I'm excited. And challenged as well. Yeah, that's a good thing. Have you on my toes. I like a challenge. I like to be intellectually stimulated. That's my
same here, my dear. Same here.
Yes. Are you being intellectually stimulated? That's far?
I certainly am.
That's great. Right. So the axiom or fourth law of motion, law 4, molecular rotation. The law says every body upon descent will inevitably tilt on its axis as a function of the distance it propagates through. Bodies which travel through a distance freely on Earth inevitably collide with the surrounding air molecules, which yields the rotations of the body on its axis as it propagates through the distance. A leaf descending from the branch of a tree rotates and twirls about on its axis as a result of its collisions with the surrounding air molecules. An orbiting planet, ascribed to its collisions with the surrounding graviton particles in space, rotates on its axis in the same way. Henceforth, using this information about the universe, we can ascertain the time it would take a falling body in the presence of the resistance of the air or the gravitons to fall. For objects on Earth, we can determine how long it would take any object in the presence of the resistance of the air molecules to strike the ground. And for the planetary bodies, we can determine how long it would take to orbit around the sun. So you see the implications there. This is given by the equation ut plus 1/2 multiplied by d over g over w, all plus r equals delta t, where delta t is change in time. Delta means change in physics. Where d is the distance, g is the acceleration due to gravity, w is the weight of the object or planet, and r is the resistance. This additional law of motion explains why the planets spin on their axes in space.
Lovely. I would love to see you 5 years from now, where somehow you have combined your quantum law of gravity and your derivative calculations to blow all of our minds. I don't know what you create with those two combined.
I've actually combined it with special influencity already. And I've been able to ascertain how a person's degree of influence changes over time, because that corroborates and falls in line with my notion that influence is not static, it's dynamic. It is ever
Yes.
changing. Influence changes as time goes on.
Yes, she did go into full detail with the theory of
Influence.
influencity. So make sure
Yeah.
if you're listening to go and listen to that podcast.
Yes.
Do you have
Yes.
any final thoughts that you would like to share that I haven't asked you in the remaining minutes?
Well, I would like to thank you for the opportunity for giving me a voice to an international
My
audience.
pleasure.
Well, the pleasure is all mine. Thanks to your brother, Mr. Adeyemi, for giving me your email address so I
Yes,
can
he
contact
did.
you, and thank you for
I told him
contacting me
not
on
to, but
WhatsApp.
he never listens to me. I'm kidding.
You got jokes. So just before we go, let me just show you some of my equations here from my quantum theory of gravity.
Yes.
This is the equation for gravitational time dilation. I know it's beautiful.
It's very beautiful. Yeah, I love that.
It's like art.
It is art.
Yeah. And then now we get into dark matter and dark energy. I explain what dark matter and dark energy is, something that physicists are struggling to explain and understand right now. So if I'm correct, I better start counting my Nobel Prize money.
You really better start. Remember to lend me a $5.
Of course. And these are my equations for gravitational framework curvature.
Oh, wow.
That's the general field equation there. Another beautiful equation.
That is gorgeous. What's the trident part?
What's the what?
The thing that looks like a trident in the top
You're
equation.
talking about
next to the A.
This?
Yeah.
This?
Yes.
That's psi. Psi. Greek.
Psi. Okay, great.
Yeah.
Okay, what's Greek the next one?
Symbol. The next one, next to it, I think is this one you're talking about?
No, the next equation down.
Down here?
Yeah.
That's the same one I was explaining to you earlier on that I said uses differential calculus to calculate the partial curvature of the gravitational framework. R mu minus 1/2.
Lovely.
Curvature tensor.
Beautiful.
Yes.
I have a suggestion for you.
What's your suggestion?
On your miniature
houses,
please, in very small letters, put your equations on there, because it's art.
Yeah, it's art. It's art.
It would be really pretty, and people would discover it. They wouldn't recognize what it was initially. And then they'd be getting all the vibration energy of all your wisdom via your miniature homes. That'd be very exciting.
That'd be a great thing. That'd be a great thing.
You got to pay me money for that, though. I came up with that myself.
It's copyrighted work.
That's what it is.
Yes.
Well, Ramone, I'm sure if you had 3 more hours, you could have gone into as much depth as you would have liked. But do you feel that you got to at least share the main aspects?
Yeah, adequate information was dispensed.
Yes, great. But I found it very interesting. I'm sure the audience will find it very interesting. Yes. I'd like to thank you again for agreeing to come on the show.
This time.
Yeah, he's come a long way, guys. I'm sorry. I'm seeing a whole new Ramone. He only moved back and forth a few times. I was very impressed. So thank you for that. Appreciate that. So until whenever the next time is we meet Ramone, I don't know. It may be me in the audience waving at him as he's picking up his Nobel Prize. We don't know when or how it's going to happen. But it's been an absolute pleasure. Thank you again, Ramone, for joining us on Conversations with Eve and More. Until next time, folks. Bye.